Good evening, everybody. I'm Saurabh Paliwal. I'm a biotech entrepreneur. I did my PhD in biomedical engineering at Johns Hopkins. And my Hopkins, yeah. What are the odds, right? Yeah, and I'm a co-founder of a biotech startup which is developing technologies for doing drug discovery and personalized medicine. So yes, I shrank the lab, and unlike the movie, it was for a good reason. We've always been fascinated by shrinking things down, whether it's accidentally shrinking down your own kids or creating a miniaturized team of spies and surgeons who go into the body. Like the vast outer space, the small is fascinating to us. Look at the UNIVAC computer from the 1950s, which took up a whole room. Now you have a more powerful computer which sits on your lap. Whether it's laptops or medical devices, smaller is better. So what could we do if we could shrink down the lab? There's a technology called microfluidics which does just that. Microfluidics is being used by researchers all over the world to do some really important things. So what is microfluidics? It means fluid flow at micron scales. A microfluidic chip like the one shown on the right can actually be produced using technologies which are very similar to the one that semiconductor industry uses to make electronic IC chips. A microfluidic chip contains an inlet, an outlet, and a channel connecting them. These channels can be 10 to 100 microns in width, about as thin as a human hair. It also contains chambers and wells where you can create chemical reactions, you can trap cells, treat them with drugs, etc. There's another very unique thing about microfluidics, which is called laminar flow. The flow in these channels is laminar flow. So what is laminar flow? If you focus on the cigarette in Humphrey Bogart's hand, the smoke that is rising out of the cigarette is initially laminar flow, and eventually it becomes turbulent flow. It is these flow patterns because of which a golf ball is actually dimpled and not smooth. So using microfluidics, you can create some pretty interesting patterns, like the stride pattern on the left, or some funky patterns like a keyboard or the Eiffel Tower on the right. Fun and games are good, but what is microfluidics really used for? I'll talk about diagnostics for the developing world, biological research, and two areas that I'm very passionate about, drug discovery and personalized medicine. Let's talk about diagnostics. Now, you're going to look at these two pictures over here, and you'll see the disparity in the facilities available in a health clinic in a developing world. So a diagnostic for this environment needs to be easy to use by an untrained technician. It should be robust so it can survive in a harsh environment, and cheap. Microfluidic chips like the one at the bottom left is a disposable polymer chip, or you can come up with innovative designs where you can actually put channels in a piece of paper. So that's a cheap, disposable microfluidic chip. It's used in research where a chemical gradient can be used to find out how yeast cells find their mating partners, or how a nerve goes all the way from the brain down to the muscles and connects to the right muscle. Let's talk about drug discovery. Despite the huge amount of R&D spending in drug discovery, you don't get new drugs coming out. Drugs fail in clinical trials. One of the important steps during drug discovery is where you treat a drug library on living cells. Today, it's done with frozen cell lines. These were cells that were obtained decades ago, have been outside the body for like 50 years or longer, and they've been frozen multiple times and have low clinical relevance. Because microfluidics is so miniaturized, now you can treat a drug library on a sample of cells from a patient. These are fresh cells, have high biological relevance, and the drug candidates have a much better chance of success in a clinical trial and in an actual patient. Let's look at medicine today. If you have the same disease diagnosis, chances are you'll get the same prescription. But each of us over here is different, and we respond to drugs differently. So we need ways to find out how to find the best drug for a patient. If someone has cancer, the doctor generally prescribes the best common drug for that cancer. If that doesn't work, they go with the second drug or the third drug and so on. It's a trial and error procedure, but it causes immense harm to the patient because of the harshness of the chemo treatment, and it's very costly. What if we could take a small sample of a tumor biopsy from a patient, put it in one of these microfluidic chips, expose them to a lot of drugs and drug combinations, and find out which drug actually works best for that individual patient, 1, 2, or 3. So the patient gets treated with the right drug at the very first time. This is better, cheaper, and faster. And if you still don't believe me that smaller is better, maybe these photographs will finally convince you. Thank you.